All right, my friends, and here's what I'm going to do this time. We're going to consider, when we mix two solutions together, will the concentration of the ions be enough to make a precipitate happen? That's going to be one of the things. It's going to be the focus of a number of problems in this chapter, whether a precipitate will form or not. So I have we only have enough time probably for 4 or 5 slides today. It's really kind of slow. What I'm going to do here is I have a problem. This is it. And then underneath the shade, I've got some guidelines, I guess. Some notes on what to do with problems like this. And then we'll do the problem. I'll turn the lights off. So up until now in this chapter, we've looked at a not very soluble solid being put into water. It dissolves a tiny little bit, and we're trying to figure out what concentration of the ions are made, what the solubility of the solid is. Well, now, this is the opposite process. This is putting ions into a mixture and seeing if the reaction will actually, and what I'm doing with my thumbs here is, if the reaction will make a solid form. So at the first, with these problems, everything is dissolved, and will a solid be made? Now the reason I was pointing in the leftward direction with my thumbs is this. When we write the chemical equation for every solubility kind of problem that we're going to have, always have the solid on the left, and then it's dissolving to make the ions on the right. Even in this case, you're starting with ions. You'll be tempted to put the ions on the left side. Don't do it, even though that's what you're starting with. Put the ions on the right, with the solid on the left. And the reason for that is because the KSP of any solid depends on the equation being written like this. Because the ions are going to be on the right, that's the products, which are in the numerator, and then there's nothing in the denominator. If you turn this thing around, you'd have to invert the KSP. We're not going to do that, so just get used to having the solid on the left, even if you don't have any to start with. See, if you look at this problem, there's no solid to start with. You would still write the equation like that. So, what we have to do to be able to solve this thing, first thing is when you have two solutions mixed together, figure out what possible precipitate would be made. And there should probably be just one combination of ions in this mixture that would possibly precipitate. Can you tell what it is? What would be our precipitate in this problem? Mixing magnesium ions, nitrate ions, sodium ions, and hydroxide ions. One combination will be not very soluble. What is it? Then not sodium. Sodium is soluble with everything. And nothing with nitrate, because nitrate is soluble with everything. It's got to be magnesium with the hydroxide. And you might want to remember that hydroxides in general are not soluble pretty much with anything. Carbonates are kind of the same way. The group 1 ions are soluble with hydroxide. Sodium hydroxide, it's up there. Potassium hydroxide, lithium hydroxide. But other than the group 1s, even though magnesium's a group 2, it's still not very soluble. So that's our most likely precipitate in this problem, is magnesium with hydroxide. Another way that we could think of that, in the book, at the end of the book, where the appendices are, we had the Ka and Kb tables on page A22 and A23. And then on the very next page is the KSPs. You would look for a combination of, if you don't really know what else you can do, look for a combination of two of these ions in this table, because this is all the not very soluble things that you would have to worry about. And magnesium hydroxide is on here. In fact, while I'm looking at this, I'll write down its KSP value is 8.9 times 10 to the negative 12. We'll need that. Okay, so after we determine what the most likely precipitate is, oh, I didn't write it down, but we know what it is now. Also be aware that you are combining two solutions, so the concentrations are going to change. Even before any reaction happens, you have a certain volume of a molarity of this, and then a certain volume of different molarity of that. They all get combined, so everything gets diluted. Watch out for that, and don't forget. So I'll take care of that in a moment. The other thing is this. We have to use the Q value. And I know that Q has come up before, and sometimes Q is confusing to people, but remember, Q is, it just tells us what the status of the reaction is. If Q equals K, that means the reaction is in equilibrium. At the beginning of a reaction, Q equals 0. And if Q is less than K, then it's going to shift to the right. That means the reaction is too reactant heavy. It's going to go to the right. If Q is greater than K, I'm pointing to the wrong things here. If Q is greater than K, that means the reaction is product heavy. It's going to shift back to the left. So with that, let's see if we can take this problem out. I'm going to move this way up. So the likely precipitate in this case would be magnesium hydroxide. And that's going to be making magnesium ions, and then 2 hydroxide. So the question is, will a precipitate form? The concentrations of magnesium and hydroxide, don't just copy them down from what you're given above. Remember, we have solutions that became diluted when we mixed the two together. So what's nice about this problem is we have the same volume of both solutions. It's 100 milliliters both. So both solutions wind up doubling their concentration. They both go from 100 to 200. So when you're, I just said doubling the concentration, didn't I? They double the volume. And their concentration gets cut in half. Yeah. So where the magnesium ion started at 4 times 10 to the negative 4th, when its volume doubled, its concentration is now 2 times 10 to the negative 4th. And likewise, the hydroxide started at 2 times 10 to the negative 4th. When its volume doubled, it is now 1 times 10 to the negative 4th. And really, that's all we have to do for this thing. If we can calculate Q and compare Q to the K value of magnesium hydroxide, that really is all the question is asking us to do. The Q equals magnesium concentration times the hydroxide squared. To repeat, Q is calculated the same way that K is calculated, but Q doesn't necessarily have to be at equilibrium, where K does. You would not calculate a K if the reaction is not at equilibrium. So, the Q value is magnesium, 2 times 10 to the negative 4th, times the hydroxide squared, notice it's squared, 1 times 10 to the negative 4th squared. And without a calculator, what does Q equal? So 2 times 10 to the negative 12. Right. This thing squared is 1 times 10 to the negative 8, times another 10 to the negative 4th, and then times the 2. So Q equals 2 times 10 to the negative 12. How does Q compare to K? Q is right here, K is right there. Which one is bigger? It's a little tricky. That 10 to the negative power gets people. Which is bigger, Q or K? K is bigger. Yeah. Yeah. This would be 0.11 zeros and then 8, 9. This one is 0.11 zeros and then 2. So the K value is bigger. So if Q is less than K, that means that the reaction tends to shift to the right. And what that means is it's not concentrated enough to shift to the left. No precipitate forms in this case. If Q is less than K, no precipitate is going to form because the reaction is tending to go to the right. So everything just stays clear and dissolved, no cloudiness, no precipitate form. Anybody have any questions about that? The analysis of that. Don't lose sight of Q. If the Q is confusing to you, stop by and we'll talk after school or before school, whatever. Or you can read about this in the book, that Q-K relationship. It comes up a few times. Okay, here's another will it precipitate form kind of question. This one's pretty easy, I think. So the KSP of aluminum hydroxide is not very soluble, 2 times 10 to the negative 32nd power. At what pH will a 0.2 molarity aluminum solution begin to show precipitation of aluminum hydroxide? The chemical equation is written like this: solid on the left, ions on the right. Aluminum concentration is given to us, 1 sig fig. We don't know the hydroxide concentration, just call it X. And the question is, what does that X value have to be so that this reaction will just start to produce the precipitate? Will it shift to the left? So in order to make a precipitate, Q has to be greater than K so that the reaction actually shifts left. And Q, remember, is calculated by taking the aluminum concentration times the hydroxide concentration cubed, and that has to be greater than the K value. And the K is given to us right there. So go ahead and plug the numbers into it. The aluminum concentration is 0.2. The hydroxide concentration is X, and it gets cubed. And that Q value has to be greater than 2 times 10 to the negative 32nd. Now, when you solve for X, it's pretty simple. That 0.2 just moves right over there. And take the cube root. And I don't know if I can remember this from memory.